Hello students. In this problem we're going to use the power of the first and second derivative to perform some analysis on this polynomial function. We're going to determine some critical numbers. We're going to look for intervals of increase and decrease. We're going to find where we have local maxima and minima. And then we're going to determine where the inflection points are and where the function is concave up and concave down. And then the last two questions we're going to answer here have to do with asymptotes. All right, so let's begin our analysis. So the first thing we're going to do is rewrite the function and then just compute the derivatives. Simply put, we're just going to use the power rule just to compute the derivatives. Now with the derivatives in hand, we're going to locate the critical points. The critical points, conventionally defined, are where the first derivative is equal to 0 or the first derivative does not exist. So I'm going to take this function here, 20x to the fourth minus 24x third, which we've determined is the derivative of this function, and I'm going to set that equal to 0 because I'm going to look for where we have horizontal tangent lines to the graph of this function. I will factor out the greatest common factor. That'll make my analysis much simpler. And then notice that if you have a product of two quantities and it's equal to 0, then one or both are equal to 0. So 4x cubed equal to 0 means x is equal to 0. 5x minus 6 equal to 0 means that if I push the 6 over and divide by 5, x is equal to 6/5. So I'm going to plot those critical points on a little number line here, and I'm going to make a sine graph. And I'm going to indicate that I'm doing the analysis on the first derivative here. That'll give me information about the original function. So I'm going to use some test points to do my analysis. There are other ways, and I'm going to show you actually a geometric way when I analyze the second derivative. But right now, let's just use test points. So if I look at the graph here, the test points I'm going to choose is going to be something less than 0, so I'll pick minus 1. I'll pick something between 0 and 6/5. Since 6/5 is greater than 1, I could pick 1. That might make things simple. And then I'm going to pick something greater than 6/5, so I'll pick 2. All right, so those are my test points. Now I'm going to plug those into the first derivative. Notice I'm plugging those into f prime because I want to know where f prime is greater than or less than 0. That will tell me where f of x is increasing or decreasing. So f prime of 1, minus 1. Now if I plug minus 1 into this function here, I like to look at this one here. You could do it here, but I find it simpler to look at the factored case, and I'll show you why. If I plug minus 1 into this 4x cubed, that's going to be a negative number. I don't care what number it is. I just care that it's positive or negative. So it's negative. If I plug minus 1 into here, I'm going to get a negative and negative. That's going to give me a negative number. So I have a negative times a negative. That gives me a positive. So I put a plus sign here. If I plug in 1, this number 4x cubed is going to be positive. If I plug in a 1 here, 5 minus 6, that's negative. Positive times negative is going to give me a negative. If I plug in 2, I'm going to get 2 into 4x cubed is going to be positive. 2 into 5x minus 6 is going to give me 10 minus 6, which is a positive number. Positive times positive is positive. And that's how you can do some sign analysis. All right, so now that I know that the first derivative is positive from minus infinity to 0, I know that the function increases from minus infinity to 0. Between 0 and 6/5, the first derivative is negative, so the function decreases between 0 and 6/5. And then from 6/5 to positive infinity, the first derivative is positive. So from 6/5 to positive infinity, the function is increasing. All right. Now, armed with that information, I can determine whether or not I have a local max or local min, and I'll use the first derivative test for this case. I could use the second derivative test. I could take these numbers and plug them into the second derivative, but I'm going to use the first derivative test. Since I have this analysis here, it's just much more efficient to do it that way. So remember, the first derivative test tells you that if f prime is greater than 0, goes from greater than 0 to less than 0, then you have a local max. You can remember it in terms of words. I just find it easier just to remember by looking at the picture. If you just look at the arrows, this looks like a max, right? It's increasing then decreasing. That's a local max. Then it's decreasing and increasing. That's a local min. All right. Now we have that information. Let's look at our second derivative, and we're going to locate some inflection points. Actually, what I'm going to do here is I'm going to try to locate candidates for inflection points. So to locate those candidates, we look where f double prime is equal to 0 or where f double prime does not exist. So again, I write my second derivative down here, set it equal to 0. And then I factor out my greatest common factor, 8x squared, and I have a 10x minus 9 here. So I set both of these equal to 0, so 8x squared is equal to 0, and or 10x minus 9 is equal to 0. And then 8x squared is equal to 0 when x is equal to 0, and 10x minus 9 is equal to 0. When I push the 9 over and divide by 10, I get 9/10. So those are my two candidates for inflection points. And I'm just going to do all the analysis at once here. So if I plot 0 and 9/10 on a number line, then I'm going to pick as my test points -1 because that's left of 0. I'll pick 1/2 because that's between 0 and 9/10, and I'll pick 1 because that's greater than 9/10. When I plug -1 into the second derivative now, remember this is analysis being done on the second derivative because that will determine where we're concave up or concave down. F double prime the -1, if I plug, now look, if I plug just about any number into this thing, any real number, into 8x squared, I'm going to get a positive number. So again, I'll go back to the factored second derivative to do my analysis. So if I plug -1 in, I get into 8x squared, I get a positive number. A -1 into 10x minus 9 is going to give me a negative number, because a negative minus a negative. Minus 10 minus 9 is going to be a negative number. So positive times negative gives us a negative on the plot here, on the sign chart here. 1/2 was my other test point. 1/2 into 8x squared is going to be positive. 1/2 into x here is going to be 1/2 of 10 is 5. 5 minus 9 is a negative number. Negative times positive gives us a negative. So I have two negatives in a row. So I'm concave down over this whole interval. At 1, my other test point, 8x squared at 1 is going to be positive. 10x minus 9, if I plug 1 in for x, I get 10 minus 9. That's a positive number. Positive times positive gives us a positive. So we'll be concave up on this interval. Now, I could have done this without test points. I could have done this geometrically. If you look at this factored form of the second derivative, notice you have an 8x squared. That's a parabola. It touches the axis right here at 0. And it's always positive then in that case, or it's at least non-negative, right? Okay. Then 10x minus 9 is a line sloping up this way, and it crosses the x-axis at 9/10. So it looks like this line right here. So now that I have that those things graphed, I'm going to break them into the three regions where where I have the two inflection points, or candidates for inflection points. And notice that 8x squared is positive on this region and positive on this third region. And 10x minus 9 is below the axis, so it's negative on this region, negative on this region, and positive on this region. And then I just multiply the signs, right? Positive times negative gives us a negative. Positive times negative gives us a negative. Positive times positive gives us a positive, and I get the same sign analysis. So you could do these geometrically if you just want to sketch out these graphs on top of these sign charts, and then you'll see what this sign analysis is if you don't want to use test points. Some students find this more efficient than using test points. All right, now that I have all that information, I'm just going to enter my answers. So here are all my possible answers. In summary, let's focus on the asymptotes here. Now, if to find the horizontal asymptotes, we look at where x, that's the horizontal axis, goes to positive or negative infinity. And if this 4x to the 5th is going to dominate this 6x to the 4th. So if we're going to positive infinity, this is going to go to positive infinity. And if we go to negative infinity, then this is going to dominate this term. So we're going to go to negative infinity. If x goes to negative infinity, then the whole function is going to go to negative infinity. So you can already start to get a feel for what the graph is going to look like. And I just kind of sketched like a rough sketch down here. So, right, we're increasing, and then it flattens out, right? That's what this 0, where we have no change in curve, no change in concavity. That's really what that's telling us, is that it's getting flat here. And then we go to concave up at 9/10, and then we're increasing from 6/5 onwards. So you can see that this is what the graph's going to look like. So since we don't change concavity here, we're going to take out 0 as an inflection point, and that's reflected here in part H, where I say that the inflection point is just 9/10, and I just indicate that it's concave up from 9/10 to infinity, or concave down from minus infinity to 9/10. If you want to see a plot of the function, here it is. And I'm doing this in Sage Math cell. This is what it looks like when x varies from -5 to 5. We could zoom in if you like. I'll make that -0.5 to 0.5. And you start to see what's going on here. And you can zoom in to your heart's content. That's the nice thing about these graphing utilities. And you can see how it's just starting to look similar, but it's flat. Now the graph, yes, tells us the behavior of the function, but it's really the analysis here that not only gives us confidence that that graph is correct. It's not really the point. The point here is to understand the concepts of increasing, decreasing, and concavity, curvature. Okay, that's the point of doing this kind of analysis. It's not just to graph a function. We have graphing utilities for that. The point is to understand the analysis and to understand the calculus concepts that provide us the tools to perform this kind of analysis. Okay, good luck.